for those people who don't come to the virtual session but still need to know this. Okay, so this virtual session is about central tendencies and mice. It is the last science-y thing that we are going to be doing. And not science-y thing, excuse me, statistics thing. My brain is all over the place today. So here's what we're going to do. How do I use Nearpod is the question. Objectives. Okay. I think I do that. That's weird. Okay. Are you guys seeing objectives? I hope so. Bonnie's nodding. Good. Okay. We are going to review central tendencies, right? Some of these things you might remember from math: mean, median, mode, range, domain, other things, maybe. We're going to expand. We're going to talk about more complex ones, variance and standard deviation. We're going to apply to a real world scenario of mice tail length. And then we're going to discuss the best ways to use central tendencies, right? So again, we're going to be getting at sort of problems with reporting data, which honestly, when you leave this class, I want you thinking, wow, I should be questioning every single thing I ever see in my life, because that's what I want you to get out of this, right? It's true, you really should be. So we're going to start off with an open-ended question. I feel like there's got to be an easier way to navigate out of these things, but we'll just go with it. Oh, there's an arrow. Cool. So, oh yeah, look, it's going to show your answers. So maybe I won't share. Stop share. I don't know. This is going to be a complex technology managing moment for me. You should see on your screen a question, right, asking you to define as many of those things as you can. Mean, median, mode, and range. So take a second right now to submit an answer. Hopefully you know what at least one of those things is. And if you are not seeing this, let me know. I'm assuming it's because everyone's ferociously typing. Oh, I can switch to student view? Okay. Love technology. Maybe. Okay. So awesome. I see one answer from Briley. So I'll wait a little longer because I know I'm asking you guys to define a lot of things at once. All right, good. I'm seeing a bunch of answers populate in here. 50% participation. I'm going to go ahead and hide people's names, but then we're going to go back to sharing my screen. I figured out how to do this now. Be proud of me, guys. Technology management. Okay. So what do these things mean? We might still be getting a few more people typing answers in. Come on, Zoom. There we go. But mean is the average. Most people said that. It's the average. Median is the middle. Mode is the number that occurs the most. Range is the difference between the highest and lowest numbers. Right, I see pretty much the same answers from everyone who defined any of the words that they know. Yeah, mode is just the most frequently occurring, kind of a weird one, not frequently used, right? It's usually like a math one where they make you know it and then otherwise, right? So I really like the answers here. So I think you guys should be able to see that now because I just shared it with you. But really, these are pretty common words that you're probably used to hearing, right? You may hear the word average instead of mean, but you hear about averages all the time. That's actually what's going to be the focus of today's topic, is the average. But first, we're going to talk about more complex central tendencies. That's what CTs stands for. So we know of something called the variance. I say we because you're about to know about it. That's the formula there to the right, which is, you know, maybe not the easiest formula to understand in the world, which we'll break it down in a second. But this shows how far spread out the numbers are from the mean. So in other words, your mean is 5. Well, if you have a negative 400 as one of your numbers and a positive 900 as one of your numbers, your variance would be very big, right? That would tell you, as someone reading the data or understanding what's going on, oh, their numbers were kind of all over the place. So the way that you actually determine this, right, is you take the mean of your data set, which is represented by this X with the bar over it, and you subtract that from a number in your data set. You square it, you take the sum of all of those, and then you divide by the sample size minus 1. Sounds really complicated. It's really not that hard. But let's say you had 15 numbers in your set, right? You would find the average of those numbers, and then each number you would subtract the average from it, square it, add them together, and then you would divide by 14. There are lovely websites that do this for you, which is great. Should you be taking notes? I will be posting this PowerPoint. It's actually already posted, Georgia, so I would take notes if I'm saying something that's not written down. However, you will have access to everything that's showing on the screen. So for example, if me telling you about the big range of numbers was helping you understand variance, right, that might be something you want to write down. But that's how I think of variance. The bigger the range, the bigger the variance, right? If numbers are really far away from each other, it's going to cause a big variance. Now, what does that mean, right? It might not mean anything. It might mean something. It kind of depends on the situation. But it's important to know, right, that if you have a big variance, you should be thinking about what that means. And you might come to the conclusion that it doesn't matter. You might come to the conclusion that, oh, my 5 years of life that I just spent on this experiment are a waste of my time, right? Which is hopefully not the conclusion you come to, but it happens. So moving onward, standard deviation is another really, really common one. If you take advanced math classes, / you major in a science or take a science in college, you will have to do this. Standard deviations is a measure of variance, right? So it's another way to report the variance. In this case, it is the square root of the variance. It means the same kind of thing. The smaller the number, the more close to the mean all of your data is. The bigger the number means that there's a lot of variance, right, or a big difference from the mean. So it's another way of interpreting how close are your numbers to the average or the mean. It's basically the same formula as variance, except in this case, you take the square root of that. Again, there's handy dandy websites that will compute your standard deviation for you. And usually, for the most part, when you have a huge standard deviation or a big number, right, that usually means that your data is probably not the best. Again, there may be situations that it would not matter, but most of the time, if you're getting crazy numbers all over the place, that's not good, right? So think about an example that you guys will understand, a test. The statistics quiz, right? My standard deviation for your statistics quiz is pretty low because most people did pretty bad all around the same place of bad, right? Most people got like a 60% on it as the average. And most people were within a few points of that, right? There weren't people getting zeros and people getting 100. Most people were around 60. So that is good, except that I would like the average to be higher. So I'm probably going to be modifying a few of the questions in the future, right? By the way, if you're upset about your quiz, please email me. I had a few people do that, and I was able to help them with some stuff they didn't know and add points back to their quiz, right? So that's always an option. But my standard deviation was pretty low because all of you guys got pretty much the same score. Okay. Those things will, uh-oh. Okay. There's a page happening. I thought maybe it was going to be like an earthquake drill or something. I was about to continue teaching as I sheltered. Okay, so then we come to this point, which is really, if you don't take anything away from this entire lesson, this is what I want you to understand. How good is the mean? We love the mean. This is my favorite sentence I've ever written for this class. We know what the mean means, right? If you say the average of something, people go, oh yeah, average, cool. If you start talking about standard deviation, people go, okay, I don't really want to talk to you anymore, right? They don't know what that means. We talk about averages all the time. In everyday language, in math, in science, right? It's something that we're very familiar with, so it's easy for people to relate to. So if there's a way for you to present an average on your research, you should definitely do it, because people will go, I understand this. However, is it always the best way to represent data? Right now, that's kind of an open-ended question. You might be thinking, yeah, it's the average. It's good. It's always good to know. You might be thinking, no, it's not always good, right? You may be thinking, I have no idea. Well, we're about to discover. So we're going to take a hypothetical mouse situation and we're going to apply this concept to it. So we have two types of mice. We have our control mice and our experimental mice. Look how cute they are. No mice were harmed in the making of this PowerPoint because they're little plastic ones or furry ones, whatever they are. So the question that we're going to be answering is, does this mutagen matter? Basically, I took my mice, I divided them into two groups. My control mice are in one cage, my experimental mice are in another cage. My control mice, I fed regular mice food, right? What do mice even eat? I don't know. Whatever, I fed them regular stuff. Experimental mice, I gave them this mutagen, right? Or really like a poison, essentially, a chemical, to see if it would affect them, right? Because I think from doing research and doing all this other work that this mutagen is causing them to have a different tail length. So I want to design an experiment to see, is that true? Right? Of course, being a good scientist, my null hypothesis, right? I would assume, no, there's no difference between regular mice eating a regular diet and these mice eating this mutagen, right? Or something that's meant to mutate their DNA, basically a poison. So here's two examples of mice from each group. Now, if I saw these mice, I had just pulled them out of their cage and I looked at some of the experimental mice, I'd go, ooh, it does look like this is having an effect, right? The experimental mice tails are short. So that seems like maybe something's going on there, right? So then I would start to analyze my data. Here is the data that I collected for the control mice and the experimental mice, which, by the way, if you guys were here in person with me, I would have made you measure fake mice tails. So we skipped that. I did that part for you. Here's what their tail lengths were. Now I need 2 volunteers to calculate the average of the control mice tails so that we can confirm that it's the correct answer. So if you would like to do that and it's not too hard for you to get to the chat in Zoom, I know, technology management, 2 volunteers, Georgia's gonna do it, and Briley's gonna do the average for the control mice tails. And then we need 2 people to do the averaging for the experimental mice tails. Any volunteers for that one? I might have to select some people. Bonnie, could you help us out with averaging the experimental mice tails? Okay, Bonnie's gonna do it, and who else is even, let's see. What about Abby or Colin? Would one of you guys want to help also calculate the experimental mice tail length average? Right, how do we calculate an average? We add them all up and divide by the number there are. So we'll just take a couple seconds here. If you need something to do right now, try to calculate the average of one of those and see if you get the same number as your wonderful classmate volunteers who are also averaging. And I'll be quiet because averaging is hard to do when someone's talking. Thank you, Colin. All right, so Bonnie is telling us that for experimental mice, she got 5.4 as the tail length. Georgia got for the control mice 5.5 or 5.49. Rounding up is fine. Briley confirms that we got 5.49 for control. Okay, good. So experimental 5.4, control 5.5. I think I made a slide where I was going to ask you to do the averages, but then the picture was small. Let me see. We'll go to the next one and see what happens. Okay, this is a collaborative board. No. So we're actually going to move past this one because we just did this, right? But you guys are correct that we have 5.4 equals experimental and 5.5 equals control. Okay, sweet. So, I thought that said let's celebrate for a second. I was like, did I write celebrate in this? I didn't. So what does that mean? Well, let's think about it. First of all, is that really that big of a difference? 5.4 and 5.5. Let's say that you didn't get to look at the data, right? Because I did a really bad science study and I just published the averages. Would you think there was a difference if I said, well, my control mice got 5.5 and my experimental mice 5.4? Those were the tail lengths, the average tail lengths. Bonnie says no. Yeah, you would go, okay, yeah, that mutagen's doing nothing. However, if we look at the data, is that what we see? I was prepared to not be able to easily navigate. If we go back and look at the data, which you can only see in Zoom right now, but you might remember it, right? Looking at the data, is that what we think still? Does it look like there's not something happening here? Colin says, yeah, it's a lot different than the control mice, a lot more range. Excellent. So we're seeing tails of 8.8, 9.5, 1.8. We're seeing a huge range here. Tiny tails and super long tails. Whereas in our control mice, they're all kind of the same. 5.4, 6.1, 5.8, right? They're all kind of similar. So in this case, is the mean telling us something here? It's not, right? It's telling us that it has the same average, but the numbers are not at all the same. So if you had reported, yeah, there's no effect, that would be wrong, right? There is clearly some kind of an effect. So now we're going to talk about representing this mathematically. So if you go back to your Nearpod, at the very least, I'm making you guys stay awake because you got to go to many, many tabs here. I want you to draw a graph of what you think this would look like. Right, and I tried to put the data in the corner. I think you can click on it, yep, and you can see it much bigger if you need to see the data again. But what would a graph look like for this data? I'm not going to give you any more details other than what would the graph look like. It's going to be very vague. I'm interested to see what you guys will do. And if you're struggling with graphing this because I gave you vague instructions, you are correct. Ooh, I see one graph. Control mice versus experimental. Okay. You guys should be able to see that. I shared that one out. We got a few more coming in. Here I just see the makings of a graph. Okay. Experimental control. Okay. Lots of people setting up their graph, but then keeping their graph blank. So let me take someone's beautiful setup graph here. This is what someone turned in just now, which is technically kind of a graph. Experimental control, we have our axes, right? Well, our experimental mice, the average is going to be where most of the data points are clustered around the middle. So it's going to look like this. If this is 5 point, what was the average? 5.5, something like that. By the way, I'm in Zoom right now if you can't see what I'm doing because I don't know how to do this in Nearpod. I don't think I can draw on your drawings in Nearpod, which would be cool if I could. So our experimental mice, the mean is clustered around 5.5 and most of the data points are around that, right? They were like 6.1, 5.8, all pretty close to that. Our control mice, on the other hand, we had a bunch of points over here really low, and then we have a bunch of points over here that are really high. But the average is still 5.5, because when we take one high side and one low side and average them together, we're going to get 5.5. So we actually see two giant peaks in our, oh, I did this backwards, I'm sorry. I read your numbers and then completely did my own thing. So we will quickly say control and experimental. I kind of did those backwards, I'm sorry. Beautiful graph setup by someone here and I just completely ruined it. So we would notice in our graph of our experimental mice that we have a big range, like you guys said. It's probably easy to see that when we only had, what, like 10 numbers? But if you had 700 data points, right, you might not easily go, oh, this is really different. It might help to graph. And of course, it might help to have the computer graph for you, which I know a lot of you guys are thinking, does a computer graph for me here? So good job if you tried to draw any kind of graph there, right? But really, I want you to be thinking about those curves on the graph, right, representing where most of the points are. Okay, so now, based on all that stuff that we just said, based on the graph, we kind of talked about this a little bit, but now you're going to write your own answer to this question. Is the mean the best way to explain this data? Why or why not? So much technology management. So coming up with your own answer, which some people already said something, right? So you're welcome to say what you've already said. I just want to collect it in Nearpod here. But I'm seeing a lot of no's. Oh, I just shared an answer that I really like, which we'll talk about why in a second. No, because IDK, is that you, Kobe? I have student names hidden. It is, I knew. You're the only one that says IDK. So a lot of people said no, but then didn't explain. So the one answer that I did choose to share here, although everyone's answer is correct because everyone said no, is that this person said the mean should be looked at alongside the other forms of data, such as range, median, and mode. Right? That's an excellent answer because that's getting at the concept here that why would you only report one thing, right? We would never just say, well, we're only going to do the mean. No, we would tell you about the median and the mode and the range and this other stuff, right? If it was a good science paper. If you see somebody who's using an average to prove a point, you should be very skeptical, right? That probably means their average is skewed in some way because of something. So moving on up. This is going to be a really hard question, but I want you guys to think about this one and draw as many graphs as you can. I think it lets you just keep submitting, I hope. What would a graph look like other than the one that we just saw, where the mean is not a good representation of the data? So this is taking a concept and you're making it visual now. What would a graph look like where if you found the mean, it would not tell you anything about the data? Bonnie, all over the place. Indeed. Oh, I was trying to participate with you guys and draw, but it won't let me. I was going to submit some. So let's see what kind of graphs we're getting. Ooh, I like the spaghetti graph. Someone drew a just blob of spaghetti. Yeah, right? If your data is all over the place, a more accurate representation of that, right, might be a scatter plot. Ooh, this is a nice, beautiful scatter plot here, which I've hit everyone's names, so I don't even know. I'm just like shouting out everyone I see. These are two great examples. Whoever did green and red, straight up and straight across, that's a great one as well. Oops, there we go. Let's see. What's this one? This one has data off the graph. Well, yes, if your graph doesn't have data in it, it's not going to have a good average. That is true. So I'll give people a couple more seconds here, and then I want to show you a few other options. Because this is a hard concept to take an abstract concept and make it into a visual representation, right? So here is what you guys are seeing, some of the ones I shared out. Now I'm going to draw my own graphs here. So really, what you should be thinking is any time that the data is spread out, like Bonnie said, all over the place, right? So the scatter plot was a great one. This is a great one here, this green line, because this means that the mean is going to be right in the middle. However, it's not going to take into account the range. Same with this. We're going to have extreme low values and extreme high values. The mean is not going to show a good representation, right? Another one that I didn't really see too many people engage with is anytime you have these like clusters of data in different points, so you can have these sort of humps, right? A mean would not represent this data well because the mean would be somewhere in the middle and would just completely exclude these really high and really low points. Also, any kind of parabola shaped thing, right? The mean is not going to tell you anything in this case. So just keeping that in mind that this is based off of actual math concepts, right? But it's true. Your data may not be well represented by a mean. So, knowing that, spaghetti, those graphs. This scatter plot is an excellent example, right? The mean would be somewhere right in the middle and wouldn't tell you anything about the other points. Okay, so moving on from there. This is why I wanted to use Nearpod, by the way, so that you could draw graphs. That was the whole purpose. So now what you're going to do for your assignment is kind of abstract. You're going to create your own data set of at least 12 points. Now, you can just make up random numbers. You could make up your own experiment, like I did with the mice, right? You could have your own version of that. You're going to have at least 12 points, and you're going to describe which central tendency is the best to analyze your data set and why. So I know you're coming up with your own data, right? So you could make it have a huge range, or you could not. You could make the mean work for you. You could say, no, I think the mode is a better representation, blah, 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 blah. To get full credit, you're going to have your data set, a graph, and a description, right? So you're going to say, my data is best represented by the mode because 7 out of 10 of the numbers were the same number, and I think that's a good representation of blah, 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 right? Then for the second part, you're going to calculate either variance or standard deviation. You're welcome to do both. And you can hand calculate them if you want. Those formulas are definitely accessible to you. Or if you check out this assignment in Canvas, I did link you to 2 websites where you can type in your data and it will calculate it for you. So you can choose to either hand calculate or have the computer calculate for you. I'm fine with either way, right? I don't care if you can do it by hand. Particularly for this class, I care that you can find a way to get that information. And I should add in here too, to explain, but that's fine. I won't. I'll make people explain next year. And you're going to calculate the mean, right? If you didn't do that already in the first part. Like let's say you said the mean sucked for your data, well, you're going to calculate it anyways, and you're going to show me that it sucked. And not only that, but when you look at your variance or your standard deviation, right, it should make sense in terms of if you have a big number for your variance or a big number for your standard deviation, that means there's a lot of variety in your data. Usually that means that the mean will not tell you much. So notice those patterns, right? You might not see a pattern because you only have 12 data points. Maybe your data isn't well represented by the mean or anything. That's also possible. Okay, so really the main points of today were for you to understand, right? Part of being a scientist is figuring out how to represent your data so that 1, people can understand it, and 2, it actually shows what your data is doing, right? You don't want to say the average of something is this, and then that doesn't tell you anything about your data. You do not need to write down this assignment, right? This is in Canvas. I just wanted to go over the directions a little bit. Again, feel free to try to calculate variance or standard deviation by hand if you'd like to try that. If not, use the calculators. And if you can explain what they mean, that's great. Otherwise, I'm not going to take points off if you don't. So I'm going to end the Nearpod lesson, which I don't really know how to do. Maybe I just close it. Yeah, I'm going to go with that. So, oops. Does anyone have any questions before we exit this virtual session today? Questions about the class, what you're supposed to do right now, other things related to the class? I'll take that as a no. Oh, Bonnie, you couldn't get it to work? I'm sad, but you get the idea. Colin's like, okay, bye. Okay, well, Bonnie, if you want, I can send you the self-paced one. You could go through it by yourself. It's not really the same. But otherwise, I will see you guys next week. And please email me if you have any questions, right? Remember, I'm here to help you. So even if you're like, I did bad on this, how can I fix it? We will talk about it. So you got to start that conversation. Otherwise, I will see you guys next week.